Welcome back everyone, and we have been talking about Bohr model atoms. We've actually been talking in a bigger sense about foundational ideas in chemistry, and Bohr model atoms are one of those foundational ideas. They help us to represent reality, and today I'm going to tackle the question of how do you solve for an ion using a Bohr model, or you could say, what are Bohr models good for? One answer to that is diagramming reality, but another answer to that is figuring out what charge an atom will eventually get by gaining or losing electrons for stability reasons. So this is the topic that we're covering today. I did go over another screencast on exactly how to solve for a Bohr model atom, and I've got a link to that set up right now in this current screencast, but let's go ahead and get started with the new information. Okay, and so assuming you know how to draw a Bohr model atom, this is an example of that over here, of a Bohr model, I should say. And so that's the Bohr model for magnesium. This is the information that you would see from the periodic table. One thing you can do that I find to be helpful is to visualize a number line. So that's what I've got written out here, where the starting location of this number line is going to be the number of valence electrons that we start with. And then what happens is we have two possible goals. So here's our first, and here's our second. What does that mean? That means for the atom to become stable, it's going to have to get down to 0 or 8 valence electrons. So in the case of magnesium here, what's going to happen is the atom actually will lose electrons because it's going to go to a more energetically favorable state. If I want to personify the atom, I would say the atom wants to have a filled outermost shell. Now we know the atoms don't really want anything, but just roll with this for a moment. We're going to say that if the atom loses these two outermost electrons, then this shell, this second level right here, energy level or shell of electrons, is going to be a filled solid shell, and that makes the atom much more energetically stable. And so that's actually what's going to happen is you lose electrons, or the atom can gain electrons, and that's what we're seeing here, is that we're going to lose 2 electrons. If you look at my diagram, it's kind of like saying, well, what's easier to do when you start out at 2? Is it easier to drop down 2 units, or is it easier to gain 6 units, assuming it is just as difficult to gain or lose units? Then the answer is, well, it's going to take the least amount of steps to become stable. That's exactly what happens in nature, and so right here you can see that magnesium is going to lose 2 electrons. Once it has lost 2 electrons, then our job is to think to ourselves, all right, well, what does that do to the atom? That doesn't change our number of protons, so we can go ahead and account for that. Remember, protons have a positive charge, so I'm going to do this. I'm going to say 12 positive. Right here, I'm just going to be totaling up all of the positive and negative things that the atom now has. So I have 12 protons, and let me ask you, how many electrons does the atom now have? The atom now has 10, and they have a negative charge. Well, what then is the sum of a positive 12 value and a negative 10 value? That's going to be a positive 2. So the way we're going to write this is going to be magnesium 2 plus, like that. And so that is called a superscript up top here. Super in this case meaning above, script meaning writing. And so what we're left with, that is the overall charge of magnesium. One way of thinking about that is to say you have more protons than you have electrons, and in fact you have 2 more. So you have an overall plus 2 charge with what's going on. So let me just label what we're doing here real quick. Okay, and just to clarify what's going on here, we're talking about the total number of positive charges we have, and then we're talking about adding it with the total number of negative charges the atom now has. It originally had 12. It's lost 2 of those, so now it only has 10 negative charges to find our total overall charge that the atom has. So that's what we're doing here with these Bohr model atoms. That is the primary benefit of a Bohr model atom. Aside from diagramming reality in a bit, it's also a very useful tool for finding and understanding what the overall charge happens to be for an ion. And so let's take a look at another example. Okay, and so our second to last example to think about, if we count up the number of valence electrons that fluorine is going to have, it starts out as a neutral atom when we're doing the Bohr model atom usually. And so think about it, it's got 7 valence electrons. So would it be easiest to gain 1 electron or to lose 7? What do you think it would be easier for it to do, all things being equal? And the answer is it'll be easier just to gain 1 electron. So that's exactly what happens. In my class, when you show a gained electron, you're going to have an arrow pointing to that electron. With other teachers and other instructors, you may see something different. That's just my system. That tells me that, hey, Mr. Dukar, I know that that atom did not have those electrons originally, whatever ones have been added, and now the arrow shows those added electrons. All right. I also want to see the math, and I think it's good for understanding to be able to see the math. So let's take a look at that. We still have 9 protons, 9 positive things. We're just adding up all the positive and negative things that this atom now has. It had 9 electrons before. We've added 1 new one, and electrons have a negative charge. So I'm going to say this is the case, and we're going to end up with a charge of -1. If you were to write this as a subscript, we just write a negative charge up here. There is an analogy for this in math when we're using coefficients. What do I mean? Think about it. If we're talking about 2x, we talk about 2x. If we talk about 3x, we talk about 3x. If we talk about 1x, we just call it x, and there is an understood value of 1 there for the coefficient. Well, it's very similar for ions such as fluorine as we have here. We don't necessarily have to write the 1. It's understood that that's there. So this is what you can do with the Bohr model atom. You can find the charge of an atom as it becomes stable, as it works to get a filled outermost shell of electrons. So it'll bump into other atoms and pick up electrons or lose electrons, and this can help you to understand where that comes from and how the stability happens, and based on that, what the overall charge that the ion has later on. I hope this has been helpful. Please like the video and subscribe to the channel if you would, and leave a comment if you get a chance. Thanks for listening.